Hello everyone. Welcome to webinar on soil structure interaction for multi-storage structure with Midas Gen and GTS NX. So our webinar is on soil structure interaction for multi-storage structure with Midas Gen and GTS NX. And in this webinar, let's look at the contents. Firstly, I will introduce you to Midas as a company. Then we'll look at some project applications of soil structure interaction. We will have a discussion on the topic, and then I'll be showing a demonstration using Gen and GTS NX, and after that we will be concluding our webinar. Alright, so after the conclusion we will be taking question answers. Let me begin with the introduction to Midas. So Midas as a company was established in the year 1989, and since then the software solutions have been distributed in more than 120 number of countries. There are 540 number of employees, more than 18,000 number of clients, and more than 60,000 number of users worldwide. Midas has its headquarters in South Korea, and there are total 9 branches all over the world. One is in China, USA, India, Japan, UK, Russia, Singapore, Philippines, and lately we have a new branch office in UAE. Midas has two main business areas. One is under engineering consultancy and the second is software developments. Engineering consultancy goes on for bridges, civil structures, buildings and plant structures, geotechnical as well as mechanical analysis. So depending on this engineering consultancies, the softwares have been developed for the bridges, buildings, geotechnical and mechanical fields. Because of this purpose, because of this reason, the softwares that have been developed are more practical and accurate as required for the consultancy. Coming to partial list of Midas users, these are big companies, worldwide users. In India, their branches are using Midas software solutions as well. So you might be knowing few or maybe all of them. So these are the software solutions that make Midas the biggest computer-aided software developer in the field of civil engineering. The family programs are into bridges, structures, geotechnical, as well as in mechanical. Under bridges, we have Midas Civil, which is a integrated solution for bridges and civil structures. Like you can have any types of bridges analyzed and designed. You can have a simple slab bridge, or you can have a complicated suspension or cable stayed or extra dose bridge, easily analyzed and designed in civil. So when it comes to a detailed analysis, advanced nonlinear and detailed analysis, then we have Midas FEA software for you. So mostly for research purposes, Midas FEA could be very helpful because it's very user-friendly as compared to other analytical software, finite element software solutions. All right, coming to the structures family program, there is Midas Gen software solution, which is an integrated system for buildings and general structures. It can handle the analysis as well as design of steel as well as RC structures. The design results from Midas Gen can be further imported into Midas D Shop, which is an auto drafting and rebar detailing module. That means you can get automatic drawings generated out of the designs that you have done in Gen program. And on top of that, we can also generate bill of materials using Midas D Shop. Then is Midas Design Plus. So in Midas Design Plus, as per Indian standard, we can have footing design, RC footing design, and pile cap design done. And we can get the drawings done as well. A good part is that Midas Gen analysis can be directly imported in Midas Design Plus for that particular footing. And then we can simply go ahead and click on Auto Design and get the drawings generated along with the bill of materials. So basically, these structural solutions are completely integrated with each other. Then coming to the geotechnical family programs, there is GTS NX and SoilWorks. GTS NX, which we will be seeing today, is a 3D finite element based geotechnical analysis system. And SoilWorks is a 2D finite element and analytical geotechnical solution for practical design. We will be looking at GTS NX more, and SoilWorks, we will be looking at SoilWorks in further webinars. Coming to the mechanical field, there is Midas NFX, which is a total solution for mechanical engineering in structural mechanics and CFD. Now, why we have put Midas NFX in the civil engineering field? Well, it is because we have 3D CFD analysis that can simulate the wind tunnel test results for the buildings, also for bridges. And also, if you would like to perform some impact analysis, then that can also be done in Midas NFX. There is Midas FX Plus program, which is our preprocessor. We can have complicated geometries easily modeled in Midas FX Plus, and this model can be further used in Midas NFX, Civil, FEA, Gen, GTS, like that. So all the software solutions basically are integrated with each other. That makes Midas family programs very, very strong. And one of the examples we will be seeing today, that is the integration of Gen with GTS NX. Let's look at some applications for the soil structure interaction. So as you can see over here, these are the applications of Midas Gen. And Burj Khalifa used column shortening analysis, used Midas Gen for column shortening analysis. Then for a complete analysis and design of Moscow City Palace Tower, Midas Gen was used, Gate of Orient, and further there is Gangsa Twin Tower. Coming to the spatial structures, there is Beijing National Stadium, Beijing NUT Stadium, Jeonju World Cup Stadium, Incheon International Airport. These are just few among many examples. And it's not just simple RC or only steel structure like frame structure, but also you can see over here that complicated geometries can be analyzed and designed. Further over here in the Foshan Lingnam Mingsud Stadium, we can see this is a complete shell structure which was easily analyzed in Midas Gen program. Then there is Japan Pavilion in Shanghai Expo. This is also a shell plus solid model, and also a complicated frame structure in the Grand National Theatre, used for the Grand National Theatre analysis. So these are few applications among many, and further also we will see some more applications using soil structure interaction. Okay, so basically we are going to be talking about some programs, family programs of Midas Gen program, which can be helpful for us to perform soil structure interaction. Okay, so we have Midas Gen, which is a one-stop solution for buildings and general structures. So why we call one-stop solution? This is because RCC as well as steel superstructure as well as substructure can be modeled, analyzed, and designed in Midas Gen itself in a single model. All right, and then we have Midas GTS, which is a 3D finite element geotechnical solution in which you can perform all the geotechnical analysis required, be it dynamic analysis, slope stability analysis, seepage analysis. There is seepage, slope seepage coupled analysis as well, and many more requirements are done. Are taken care of by GTS NX when it comes to a 3D finite element modeling. Then there is SoilWorks solution, which is a 2D geotechnical solution for practical design. It's a very efficient tool. Any structure that can be simulated as a 2D can be easily modeled in SoilWorks using smart features. You can get everything analyzed as well as designed. So that's SoilWorks, which includes analytical as well as finite element solutions for slope stability analysis. And further, there are dynamic analysis, there is consolidation analysis that can be done. There are many things that are available in SOILWorks program, which we will be discussing more in detail in our future webinar series. All right, so now comes the part of understanding what is soil structure interaction. Okay. So soil structure interaction is the phenomena in which the response of soil and movement of structure influence each other. Basically, when external force such as earthquake act at a distance, neither the structural displacement nor the ground displacement are independent of each other. Okay, so unlike the superstructure, the response of the underground structure subjected to an earthquake is mainly controlled by the ground displacement. And then the ground displacement, in turn, is largely then influenced by the dynamic properties of the ground. And also its modeling method is influential. The ground then exhibits a complete non-linear behavior depending on the strength developed in the ground due to the dynamic loading, and it is therefore important for us to closely examine the non-linearity of the ground relative to its strength. Let us look into the types of soil structure interaction. It is largely divided into two. One is substructure method, that is indirect method, and the second one is the direct method. Let us understand substructure method in short. So the substructure method is basically based on the principle of superpositions. It separates two courses of interaction. Firstly, the foundation having its inability to follow free field displacement, and secondly, there is effect of dynamic response on the foundation system because of the supporting soil. The substructure method, however, is limited to linear system or linear equivalent system. The process of the substructure method is, first step, it is to calculate the free field response of the soil at the site without any embedding of the structure and analyze the soil as a dynamic subsystem. This response will be then utilized where the structure will be inserted subsequently to determine the force displacement relationship. The soil dynamic stiffness coefficients can be then simulated as spring damper system in the structural software, and then this particular thing corresponds to the evaluation of a kinematic effect. The second step is the structure supported by the spring damper system. It is analyzed by the load case that depends on the free field movement. This step is a short interaction, hence the mass of the structure and the foundation is considered. Whereas on the right hand side, we see the direct method. The soil structure system is modelized and analyzed in a single step. The extended free field is carried at the base, and the boundaries of the model and the result of the response of the interaction system is calculated from the equations of motion. This method requires computational program that can treat the soil and the structure behavior with the same method, which shall be necessarily a finite element method or a finite difference method. In this method, the structure can be modeled in a simplified way, but then in future we need to necessarily remodel the structure in a more precise way, and that will be the next stage basically. Okay, and where the okay, yes, so the remodeling is done, and in this second stage we would take the results of the motion which will be applied at the base of the structure, and that will determine the detailed answer to us. Okay, so the programs used for this type of direct method analysis must be compatible, and we'll see that in Midas GTS NX, Gen and GTS. Okay, now direct method can be done from Gen to GTS NX, and direct method completely can be performed in GTS NX, which we will be seeing today. Let us understand substructure method in more detail. Okay, so basically, let's see how substructure method is helpful in soil structure interaction. All right, so the structure engineer, they simulate the soil as springs. Okay, the soil structure interaction done by the structure engineers is by using the springs, and that's for a given column load. And then the foundation reflects the soil settlement, and the springs represent the soil pressure. Whereas when it comes to a geotechnical model, the soil is modeled as a continuum model. Either it is an elastic space or it's an inelastic space. And then we determine the corresponding soil settlement and stresses due to the column load. How is the determination of soil springs? Well, it's very simple. The K value, which is also known as the Winkler spring or modulus of subgrade reaction, and it is the ratio of pressure over displacement. So the unit is pressure over stress over length. Let's understand the foundation response. We need to understand that there is a significant difference of the responses between the Winkler spring used by the structure engineers and the continuum model used by the geotechnical engineers. And this difference can be simulated or explained in more detail by using these two examples. The first, these are actually extreme examples, and one is a rigid foundation, and we'll see this settlements beneath the flexible foundations. So we shall actually see the contact pressures and settlements between these two extreme situations. Okay, so in further slides, let's go ahead. Okay, first case for the rigid raft. On the left-hand side, we have the structural approach using the Winkler spring model that has undergone a uniform settlement and uniform stress distribution. However, in the geotechnical approach, we can see that the settlement may be constant, but the stress distribution is not. There is high stress developing at the edge of the raft. Now, by the definition of the springs at the edge of the raft, we need higher springs than the springs at the center of the raft, right? We need to catch this stress behavior wherein we have higher stresses at the edge, and at the same time, we need the settlement to be same throughout the length. Okay, so that's the issue over here. Now, let's look at the issue in the flexible raft. In case of the flexible raft, on the left-hand side, we have the case of a single set of springs, which gives us the uniform settlement and the uniform stress distribution. However, elastic theory shows that the stress distribution under the raft is going to be constant as opposed to the stresses developed in the rigid case. But the settlement is going to vary. The high settlement is seen at the center of the raft, and the smaller settlement is seen at the edge. Again, based on the definition of the Winkler springs, we would be expecting higher springs at the edge and lower ones at the center, having low rigidity. So what is the solution of these two issues? The solution is that we should not use one zone of springs, but at least two zones, and one with outermost springs being higher than the springs at the center right? So for the stiff soil, we can have the increase of outer springs by 30 to 40% compared to the springs at the center. Whereas for the soft soil, we'll have to increase almost 2 to 3 times compared to the springs at the center. Again, the stiff and the soft soil is relative to the foundation stiffness and the loading. Right, let us understand how to determine the modulus of subgrade reaction, which is basically used for the soil spring supports. All right, so the K value, which is the modulus of subgrade reaction, it can be determined using three methods. Method A is by using plate load test, but you can calculate the value, I mean, not but as such, but you can calculate the modulus of subgrade reaction value using the test results and as it is stated in your textbooks. This is actually inappropriate for lateral design because they are only applied to areas of 1 by 1 feet scale. Method B consists of taking the same values and then using some correlations based on the plate load test. Okay, this is a very crude method. Then the most appropriate method is the method C, where you can model the loaded foundation using the finite elements. And we shall be using the method C. So the geotechnical engineer will estimate the settlement and the bearing pressure at many points. We are going to be, this is about the method C that I'm explaining, all right, to determine the subgrade reaction. So what happens is that the geotechnical engineer will estimate the settlement and the bearing pressure at many points within the raft, and they will determine many K values based on the pressure upon settlement designed, and they will draw contours of the K value, and then they will determine accordingly what kind of zones to assign and which K value to be assigned to those zones. So that's how the geotechnical engineer will prepare the information to be provided to the structure engineer. All right, now in the determination process of modulus of subgrade reaction, let's look at the substructure method again. Okay, the most common structure of simulating soil by the structure engineers is the use of soil spring supports, as you agree with me, right? The substructure method as well is by itself largely divided into two types. One is where handling the structure apart from, like the substructure apart from the superstructure, with the superstructure information reflected using the load and boundary condition is applied to the top of the substructure. All right. Then the second one is handling the entire structure together, meaning the substructure and superstructure together, and then getting the results. So the first substructure only approach is used commonly. However, when we have to consider the soil structure interaction, it may affect the superstructure as well. So considering only the substructure is not useful, not that useful. All right, next is the second part that we need to understand that with this substructure only approach, we are working with the broken components of the whole structure in reality, especially when we are dealing with seismic analysis. Next, the second one is the entire structure model, and it is more common and more accurate approach if an engineer is using more advanced analysis tools like Midas Gen or Midas Civil. This can be time-saving if an engineer would like to perform direct interaction check, which we will actually see in further in detail. Why is it time-saving? This is because the entire model with loading data can be transferred directly from Midas Gen to GTS NX. So that's a specialty of Midas software solutions. All right. Let's go ahead to the direct method. And the best way to explain the direct soil structure interaction is the bearing behavior of pile raft foundation. If we look at the left side, we have the pile separated from the raft. Okay, so the raft has its own interaction with soil around it, and the pile has its own interaction with the soil around it. Okay. However, this interaction between the pile and raft is shown in the right-hand side by 4 arrows. I mean, we need the interaction over here. Okay, this shows that there is pile raft interaction, then there is pile soil interaction, then there is raft pile interaction, and there is pile pile interaction as well. And these interactions are critical in governing how the pile raft will behave or perform and understand its bearing capacity at the end. The total bearing capacity of the pile raft will be the summation of the bearing capacity of the piles and the bearing capacity of the pile raft. The pile capacity itself is the summation of the bearing capacity, the base capacity at the bottom and the shaft capacity. Okay, the raft bearing capacity is basically at the contact stress over the area over the length. And the total combined bearing capacity by the pile raft should be larger than the applied load. Yes, we need to also multiply it by factor of safety and then compare it with the bearing capacity that we have got. All right, so how is direct method used in GTS NX? Well, we get the structural model in Midas Gen, and then it is imported and analyzed with the ground in Midas GTS NX. So basically at the first in GTS NX, we need to have a numerical model created. You can actually have one single pile and get the full simulation done based on the geotechnical test and pile test and see how accurate you are getting your model. I mean, see how close results you're getting from the model as compared to the geotechnical and pile test results. All right, and this is, I mean, we need to create this numerical model by doing some calibrations with respect to the on-site test results. All right, after you're done with setting up a numerical model, then you can simulate the actual model by applying foundations and like different types of foundations like only rafts or piles and so on, number of piles and locations of piles. So you simulate the model. And when you're simulating the model, you can actually go ahead with some parametric study wherein you can simulate the different lengths of piles, the different diameters of piles, and so on. So that's a parametric study that can be done. Then based on the load combinations also, you can go ahead with the foundation design. And the load combinations could be serviceability based or ultimate limit state based. All right, so accordingly, we will perform the foundation design, and then we determine the required structural parameters. And then these parameters, that basically the K value, is then given to the structural design. Taking the results, like the K value result, the structural design is performed, as in the analysis along with these springs is done and there is structural design done. If there is any change in the structural model, then this entire thing is, this entire procedure is repeated. We are again going to be modifying the numerical model and simulate it correctly and then go ahead with getting the accurate results as required for economical design. So that's the direct method using GTS NX. Let us also understand the iterative process that I just explained you right now in a better method. Okay. Now, to determine this iterative process between the structural engineer and the geotechnical engineer, this is the slide basically. The structural engineer provides the column loads to the geotechnical engineer who has developed the model, the foundation, and the soil. The geotechnical engineer determines the foundation settlement and stress and provides the structure engineer with the Winkler springs or soil springs. Then the structure engineer run their models and find out the settlement and the stresses on the raft. They compare with the geotechnical engineer and they either close up or finish with this, or the geotechnical engineer basically needs to revise the springs and come up with new foundation settlement and stresses, and then give it again to the structure engineer. So this process keeps up until the settlement between the structural model and the geotechnical model are closing up. So that's what our main requirement is, to close up the settlements between the structural model and the geotechnical model. Okay, so that was it about understanding the direct substructure and the soil structure interaction procedure, that is an iterative procedure. Now let us look into some the applications of direct approach. So what exactly is done is seen right over here. We have our stadium in a completely analyzed and designed in Midas Gen program, which was taken directly into GTS NX, wherein we can see the raft was, or basically the foundation was modeled and the soil as it is has been modeled, and then the direct analysis has been performed. Similarly over here for a multi-storied structure, we can see how the structure was modeled in Gen and taken into GTS NX. We will see exactly how this entire procedure in the demonstration now. Alright, so before we go ahead to the demonstration, I would like to let you know that the soil structure interaction can be performed using Midas Gen only as well. But this is an analytical approach. Because Midas Gen has this automatic calculation of pile springs and surface springs based on MATLAB and REES, these are recommended actually by the American Petroleum Institute. So in Gen, we can model the superstructure as well as the substructure, as you can see here, and apply these springs to get an economical design in Midas Gen itself. However, there is a limitation to it, and that is there is no effect of group piles. So if you have got single piles spaced at an good enough distance wherein there is no interaction, so there is no effect of this group piles, then you can definitely go ahead with Midas Gen only. Okay, this is an analytical approach. Now next is another analytical approach that can be used using Midas Gen and SoilWorks. And this one actually eliminates the limitation of Midas Gen, wherein we cannot have the group pile effect. So here we have the foundation module of Midas SoilWorks, which can simulate the group pile behavior, and it will find out the spring stiffness calculations by MATLAB method itself, and we can get the results into taken into Midas Gen program and perform an economical design in Midas Gen. Okay, what we are going to be seeing today in today's webinar is the direct and substructure. Like today we'll see the direct method using GTS NX, and this is a slide wherein we can see the substructure method using Midas GTS NX. All right, so when it comes to Gen, okay, well, let's begin. Sorry. All right, so this is about the substructure method. So in Gen, firstly, we have our building as a building with the raft foundation or any foundation as we have. All right, we run the analysis in Midas Gen program. Okay, and we get the support reactions. Basically, we assign supports at all the nodes of the raft, and we perform the analysis and get the support reactions. Then we are going to go to GTS NX. Okay, this raft is modeled in Midas GTS NX, and we also model the foundation with it. The reactions that have been that we have got in Midas Gen program are directly imported in Midas GTS NX. It actually saves a lot of time in taking the results from a structural model to a geotechnical model. But in Midas family programs, because of a tight integration between Gen and GTS NX, this is done by one click. All right, so we have got the loads on our foundation, and then we go ahead and run the analysis in GTS NX, and then we obtain the displacement at each node of the raft, and we find out in that way the modulus of subgrade reaction using pressure upon the settlement values, and then this is further given into to the structural engineers and simulated as soil springs in Gen. All right, so this is the substructure method. Now for the direct method, I'll be going directly to Midas Gen program and showing how we can do it. All right, I've got the structure now over here. Okay, firstly, let me take you quickly through the user interface of Midas Gen program. All right, we have ribbon menu at the top, which is divided in different tabs, and these tabs are arranged as per the work procedure from left to right. If you want to model the structures, we use the first 4 tabs, then we apply the supports using boundary tab, then apply the loads, perform the analysis, check the results, then go ahead for the design. We can get dynamic report generated as well in Midas Gen program, which was actually shown in the first webinar that we have conducted. All right, that's about the ribbon menu, and next is the tree menu, in which the workstream menu is more important. In Midas family programs, workstream menu is really useful. You can actually see the information related to the model, and that's a specialty of Midas Gen program, wherein you can check, display, undisplay. You can see only the information in the tree menu, the workstream menu, which is related to the model that you're seeing over here. Then is the message window at the bottom, which will provide us with the information as we required, like the queries, and also we can get the errors or warnings related to the analysis performed and the commands applied. All right, so we have this model over here in front of us, which we will be taking to GTS NX for performing the soil structure interaction. All right, so the very first step in this procedure is to export our structure into MXT file. MXT file is actually Midas file which can take the structure to a finite element or geotechnical solution. And this will include the boundary conditions as well as the loads applied on the structure along with the properties. So this is actually one of the advantages or the way of integrating with our structural and geotechnical solution. So first step is to save or export our model. So let me save it. All right, a text file is generated which you can close it. Right, it will be saved. And also we require the DXF file of this structure so that the loads applied can be easily transferred to the foundations that we will model in GTS NX. So for that, we are going to be exporting our file into a AutoCAD DXF file. All right, so we'll have all elements and with a center line that can be exported. All right, let me go to that same location. Okay, so a CAD DXF file has been exported. Now we will go ahead to GTS NX. Okay. In GTS NX, this is how we are going to be simulating our structure. All right, so in GTS NX, let's firstly go to a new file. So you can actually go to a new file right from here directly. In GTS NX, actually, it's a good advantage that we can have many models open at the same time in the same window. All right, so here we are in GTS NX. In GTS NX, the first thing we are going to do is import the MXT file. So we go to Midas MXT and import our demo1 file. When we are importing from Gen to GTS, it is important to do some modifications in the Gen structural model. And important one is converting the floor loads into beam loads and nodal loads, which can be automatically done by simply going to the table of the floor loads and right-clicking on it and saying convert to beam loads. All right, and pressure loads also can be, we can get it directly in Midas GTS NX. So as you can see here, we have got the loads on our structure and the pressures as well, and we have got the boundary conditions. Okay, so this is our model. Let's look into the tree menu, model tree menu on the left side. So here we have the material properties imported from Midas Gen, that was M30 grade of concrete. And we have also the properties generated for 1D elements, that is the column which we can actually check on to see the extruded view, or we can see the rendered view. All right, so we can see the properties on our 1D elements, and also there is 2D element, walls and slabs. So we can see all that. Then further, we can go to this analysis tab and we can see over here what all boundaries have been imported. So we can see these are the constraints. Okay, I'll uncheck this to undisplay. And there are static loads. Now it's important for us to understand that we need self-weight load case separately so that we can actually perform construction stages, wherein the first stage will be to simulate the soil stresses, to start the soil stresses with the self-weight only. So we are going to be using a separate load case for that. Okay, and we have the gravitational dead load taken from Midas Gen and the live load as well. Okay, the lateral loads that are based on codes, that is WLX, that is wind loads and earthquake loads, and the response spectrum loads, those are not going to get imported from Midas Gen. We would require to apply these as beam loads or nodal loads over here in GTS NX. We can also apply specific dynamic loads, that is response spectrum loads, directly in GTS NX. All right, so these loads we can apply. For now, we are going to be using the gravitational loads itself to perform our soil structure interaction. All right, so I'll just undisplay the static loads for a better view. Yes, another one important part is in GTS NX, the MXT file imports the mesh directly. So we have our mesh over here, and we have many mesh sets over here available that have been taken from Gen. We need to put them into one single mesh set so that it will be easy for us to work with it. And we can do that by simply dragging and dropping the mesh sets and merging them. All right, now we have just one default mesh set that has been taken from Gen. If you undisplay or display, you can see that. Okay, so this is done. Next, let us go ahead and import the DXF of the entire structure so that we can go ahead with the foundation and the raft modeling. So we'll go to this import and go for the 3D DXF file, demo1, that we have saved. and we can call it into as a DXF file into a different geometry set. Alright, so now if we undisplay the mesh, we will see our geometry that we have got imported from our 3D AutoCAD DXF file. Okay, now the next part is to model the raft and the soil. Okay, so we will go to the geometry tab wherein we can do all the drawing. Now the raft that I have underneath is of a different shape. It would take a little time for me to create over here, so I am going to be importing again from a DXF file. Okay, so I again import my raft. I'll put it under the raft DXF. And you can see the preview over here and click on OK. So we have got the raft. It's actually a polygon, it's a joint element, line elements from AutoCAD. Okay, so here we go. We have our raft outline. Now let us draw a rectangle for our soil simulation. Now how big should be this free field for the soil simulation is totally dependent on your structure. Mostly by thumb rules it is said that it should be 2 to 3 times what I recommend or what we recommend usually is that we should have a size good enough that does not let the contours of your settlements or any results go somewhere closer or modify somewhere closer to the edges of the soil that you have created. Okay, so make it big enough. So I have I have a space that I've already calculated. So I'm starting with the start point of my rectangle. And before we start with drawing the rectangle, it's a 2D which will be drawn on the XY plane. We'll just change the work plane to XY itself. And then click on apply and then input the diagonally opposite corner, which is going to be 70, minus 70, which is a relative value to the first point that I have given. All right, after that, you can click on apply and close. It's always a good idea to simulate your 3D structure firstly into a 2D. If it is possible, you can firstly make it as a 2D and then you can use extrude command to create a solid geometry out of it. So it becomes very easy for us to simulate or create the 3D structure using 2D simulation first. Okay, so I've created the 2D raft outline and I've created 2D soil outline. Now I can go ahead and use extrude command. Okay, in the extrude command, can select the target object. The target object is going to be the outline of our raft. That will come under the basic selection. So we have selected the raft outline. Direction can be selected from the datum line itself. So we have the Z datum line which I've selected, and then the length. So here I'm keeping the length or basically the depth of our raft foundation as 1 meter. So I'll provide -1 and I'll put it under a geometric set of raft. And then click on apply. So we have our raft solid created. Similarly, we're going to create the soil. So I'll go to the basic selection again and select the target object as the outline of the soil. Direction will be again the vertical axis and the length. Now here I'm going to be creating 2 layers, and for those 2 layers I'm going to be simulating the soils. One will be of 5 meters. So -5, apply. And then by using the scroll button, pressing the scroll button, I can select the bottom face of the soil, then select the target as the vertical axis and provide a length of -25, and that will be actually my layer 2. And then I'll click on OK. All right, so here we have, let me just undisplay the grid. So I'll hide the grid over here. All right, now we have our geometry created under the geometry tabs, and under the raft we have two solids. Okay, one is this solid and the second one is this one. However, we would require to change the grouping of or the set of this particular solid. So what we can basically do is we can go ahead, use this geometry set 1. Okay, select this and we can include the geometry in it. Okay, so we have over here our solid, and we can actually rename this as well. Okay, we'll rename it later. Fine. So we have over here one solid and the second solid is the raft, and we have the layer 2 as well with it. Okay. And what we are going to be doing next is, firstly, let me unselect all. Okay, firstly, the next part is that we are going to be ensuring our nodal connectivity for a proper load transfer. And for that, before we go ahead and mesh our solids, we are going to be imprinting the nodes of our columns on the raft. Okay, so for that purpose, we have the imprinting tool in GTS NX. Okay, so these are actually very good smart features available in GTS NX. You can have the points, that is the points below the columns, imported on the raft, or you can have the entire column imprinted on the raft by the point. So you can use either of these two options, no problem. I'll be using the curve tool just to show you how we can do it. So now the next part is selecting the target object, which is the face of our raft. And then we are going to be selecting the tool object, which is going to be our columns. So we will go to the front view for easy selection of the columns, and there are tools over here, selection tools, like you can use this intersect by line tool and click on one location and intersect, and to finish the selection double click, and then you have got over here 39 tool objects which will be transferring its imprint on using the shortest path line, and then we can click on OK. So that is what we are going to be doing. Okay, so we have got the imprintation of our columns on the raft. Okay. Next, after we are done with imprinting, we will go ahead with the AutoConnect tool, a very useful feature in a geotechnical software solution. Okay, so in this AutoConnect feature, we can actually use a Boolean tool which will cut the raft through the soil that we have. Okay, so that there is no overlap at this location. And also there will be connection of the faces and the points so that the mesh will have a proper nodal connectivity, and with the nodal connectivity we will have accurate load transfer. Okay, so we can select everything that we have. I'll just change this to normal selection. Alright, so we have all the meshes, and we can simply go ahead and use select all tool and use the Boolean function. We have objects selected and simply click on OK. Alright, so we are done with AutoConnect tool using Boolean function, and now if you see only this layer, show only, okay, not the mesh set. Okay, now you can see over here that the raft has been cut out, the first layer. Okay, so we are done over here with cutting out the raft from the foundation. The next part is going to be going to the mesh tab, wherein we'll define the material, and we can define the isotropic material, elastic, or we have more column for the soil. We can provide over here the modulus of subgrade reaction, Poisson's ratio, unit weight, and so on. And then we can also provide the porous information, nonlinear information if there is any, and then click on OK to finish the definition of the isotropic material property. Similarly, we can define the elastic property for the raft foundation. However, over here, I will be using importing function and importing different properties that I had already created, and I can have a new ID from second number. So we have got over here these materials, and then we close it. After we define the materials, we define the properties. We have 3D properties to be defined for each layer. So we have layer 1 having the material of layer 1, apply, and layer 2 with layer 2 property, apply. And also for the rafts, we'll be using M40 and OK. So we're done with the properties, and now we close. The next important part is to define the constraints. Okay, so before that, we are going to be meshing our foundations, raft and the soil. All right, so I'll just show all over here. Okay, so the next part is to go to auto-generate 3D mesh. Okay, auto-solid meshing. We'll select the raft, and let's provide a size of 1 meter. And then we will provide the information. Now the property that we will select over here will be of layer 1. This is because we're going to be having construction stage analysis, and then we'll click on this by providing raft 1 as a mesh set, apply. And then further we are going to be modifying the property of the raft for the construction stages. Okay, so in the first construction we will have only the soil, and the second construction will have the raft. So as you can see over here, because of the AutoConnect tool and imprinting, we have successfully created a mesh that includes all the nodes of the columns. Alright, after that, let us go ahead and mesh the first layer. That will be layer 1 itself as a material, as a property, and we'll call it as layer 1 mesh set. Okay, we will provide a coarser mesh size, that would be better. Alright, so the mesh has also modified accordingly to check to take care of the connectivity. Next is the second layer, same mesh size, but property will be layer 2, and so the name. All right, meshing has been completed. Next, let us go ahead and provide the constraints. So that can be done using the static slope analysis tab. And here we have the constraint. Okay, we'll provide a name to it as support. And we will also provide a boundary set name, again as support. Very easy for us to use. All right, and then we are going to be using the auto actually instead of basic. Sorry. All right. We have the auto constraint option in Midas GTS, which is very useful. By simply clicking on OK, the program will automatically constrain the sides and the bottom of our entire solid soil. Okay, that's done. Now in the construction stages, to change the property of the raft from the layer 1 to raft, we are going to be using change property tool. All right, this will be again in the method of raft change. That's the boundary set name which we're going to be using, and we will use the construction stage actually. Okay, and in this we are going to be using this raft, and we'll provide the raft property to it and click on OK. So we have over here, as you can see from the display, we have converted our property, layer 1 property to raft property, and the next part will be to go ahead and simulate the stages. So let's go ahead with the stage set, wherein firstly we will just click on add for the construction stage and select it and define the stages. We can see at the same time what all things we're going to be activating or deactivating, and those will be the mesh sets. So let me just show you from here how we are going to be simulating these stages. Okay. In the first stage, we're just going to have our soil. So that is our soil condition, which will have layer 1, we'll have layer 2, and also we're going to be having the raft 1. All right. The raft 1 is having layer 1 property itself. And we will have a clear displacement, that is zero displacement. However, stresses will be taken or incorporated in the model. Then we'll have under the boundary conditions, we will have the support, and we will have the self-weight as a load. It's important while defining the construction stages to put the information in the activated and deactivated data. Activated as in the mesh sets that we're going to be using for stages, and deactivated when this, the used mesh sets will be deactivated. That's what you do over here. All right, so after we are done with the first stage, we'll save it and we'll go ahead to the next stage, and that is activation of raft. Okay, for the activation of raft, sorry, we'll have new first. All right, and in the second stage, we're going to be having raft. All right, and then we will put the raft boundary condition into it. All right, and then we can see over here how the raft has activated now, and then we'll save, and we'll have a new construction stage, last construction stage, wherein we will have the entire structure with us, along with the loads and the supports. So not the supports, the loads. So here we have the default mesh set that will be activated, and we will have the dead loads and the live loads. That is it. Boundary conditions are already there with us, and nothing else that we require to provide in the activated data. And then we can just click on save and close. All right, after this, let us go ahead and perform the analysis. For performing the analysis, we will go to the analysis tab and go for the general. In GTS NX, we have a great advantage wherein we can have number of analysis cases defined and analyzed at the same time. So I'll have this as a title, CS and construction stage, and there will be an analysis control wherein we'll see the initial stage for stress analysis as the soil stage. Okay, so we are done with the analysis case. Now we go ahead and perform the analysis. I'll save this as demo 1. Right, the analysis will be performed in a very short period of time. Here we are actually past the time, but I would request for your attention for another 15 minutes. We will be looking at the results and then we will be concluding with our webinar. The analysis speed of Midas software solutions is totally dependent on the hardware. So the better your hardware, the faster is your analysis speed. So as you can see over here, the analysis time is just 13.68 seconds with so many number of elements, solid elements, and there are no warnings, so we are good to go ahead and check out our results. So the results can be checked in the results tab, as you can see here. Okay, so in the results tab, we will see the result for each stage. There is soil stage, raft stage, and there is entire structure stage. So let us look at the result for the last stage itself. The results that we can see are the displacements we are interested into. So let's look at the vertical displacement of the structure. Okay, so here we go. We can see our structure. This is in undeformed position. Okay, if you would like to see the deformation, you can click here and see the deformed structure. Okay, I'll just undisplay the geometry. Okay, now we have only the mesh sets to see the results. Okay, so we have got the displacement of the entire structure. We can actually have only the raft in undeformed manner to be visible. So we'll uncheck all and just check on the raft. And here we go. This is the displacement of our raft. And we can actually see what is the displacement, maximum minimum displacement using probe results. We can probe the results, like we can see the minimum value, which is minus 14.3 mm. I'll just change the unit system. You can change the unit system at any point of time. So as you can see over here, the highest displacement in the negative direction, downward direction, is 14.31 mm. And if this is within the limits, then you can definitely go ahead. If not, then you can increase the thickness of the raft, or you can add some piles at such locations. All right, so you can see over here the contours formed for the displacements, and accordingly the K values will be taken out for the structural analysis. So this is one result, probe result. Then we have the ISO value surfaces as well. Can make a lower part, and you can actually see the limit, provide over here the limit, that if you would like to see the result from the highest 14.31 mm to minus 10. And there you go. This is the area where, if at all it's not permissible, then you can go ahead and add some more piles, or you can do some modifications in the foundation. All right, so this is the ISO surface results that we can get. All right, now let's also look at the layer 1, layer 2 results. So this is how the results are variating with the help of the ISO values. All right, and further we can also go ahead and extract the results using the extract tool. You can look at the displacement. You can check the teaser, that is vertical displacement itself, for the entire structure stage, the last stage that is. You can select the nodes for which you would like to check the results for, or you can put the like in order of the steps, let be in steps. So we'll see the nodes, and here we can select the objects. So we can go to the top view from here, and we can go in the front selection only view option, and we can like make a box around the nodes for which we want to get the results, and then accordingly we will take, I'll use this polygon selection. Okay, this is roughly that I've selected these nodes, and then for these nodes we can go ahead, click on table, and here we go. We are getting the results for all the nodes in the form of table, which we can export into Excel sheets, or you can even directly copy and copy from your keyboard, Control C and Control V in the Excel sheets. And with the help of these, we can go ahead and even use the space special option, and then we can just modify this information. Okay, so basically we can get the displacement values from Midas GTS NX and then use it to find the modulus subgrade reaction, which will be then further utilized to apply the point spring supports in Midas Gen program. All right, so that is it about the results which can be extracted from GTS NX. There are many more results that we can get as per our requirement. Okay, for example, in the results tab, we can get the solid stresses. So there is von Mises stress that we can get. And we can also get the strains, equivalent strains, effective plastic. And this can be done for every stage. So you can actually simulate excavation also in this, and you can create your own stages. All right, so here we go. We are done with checking out the result for our entire structure. So basically, there was ease in modeling in GTS NX as well as in Gen. We have seen how easy it can be modeled in previous webinars. Okay, and further we have got a direct integration between the structural solution and the geotechnical solution. Then we can see the auto constraints that was done in GTS NX, which is a time-consuming process as compared to other programs. And because of this ability, because of the ability of Midas Gen and GTS programs to integrate with each other and have the soil structure interaction, we can get an accurate structural analysis performed and get economical designs. So these are very few of the concluding topics that we have for today's webinar session. All right, so let us get to GTS NX and let's see the results. All right, so we have let's see what is the difference between the results with the soil structure interaction and what we have in Midas Gen program. So as compared to only the dead loads, we are going to look at the results. Let's firstly look at the probe results of our displacement in the Z direction. So we have the TZ translation, and we can simply click on the nodes. So this is minus 6.3791, as a displacement of this column, and then we'll go ahead to Gen. Okay, in Gen, we have our results. So we'll see the displacement. Okay, so displacement, now we would like to check the displacement for the combination. Of course, there will be difference in the results. So we have the self-weight, the superimposed dead load, and the live load to be combined. So let's look at the load combination that we have, that we can create in Gen program. All right, so let me create one. Okay, so we have the self-weight and superimposed dead load and the live load over here. And let's look at the results. DZ displacement and the value. Apply. Okay, let me change this to mm. Okay, so basically because of the fixed support, we're not going to get any support results from here. However, if you look at this, it's coming to almost 9.7. Not 97 actually, it's very small because of the rigid foundation, a rigid support condition that we have provided. Let's look at the forces in that case. Okay, that's what we actually should be checking. So we have the moment diagram. Let me only activate one column. All right, so this is the result. Similarly, let's look at the result in GTS NX. So we have over here the beam element forces. So we can see the bending moment now. Okay, and the bending moment for our column. Okay, let's look at the element. Activating only the default mesh set. Seems okay, so this is the result that we have. This is again in kilonewton mm. Let me change it to kilonewton meter. Okay, so we have got our result over here. There's quite a lot of difference between the results from Gen and GTS NX. Let me get the correct. Looking at the actual forces as well. Okay, so basically there's a huge difference between the actual forces as well. And you can also compare for the beams. Alright, so we have got some more questions. However, because of less time, we are going to be ending the session now. And we will get back to you with your questions by emails itself. Thank you very much for attending the session, and please do attend our future webinar series as well. All your questions will be definitely answered to with the help of emails.